Hello everyone, my name is Tomasz Czerwenka from the CCDC, and welcome to this video tutorial demonstrating the molecule overlay functionality in Mercury. The molecule overlay function calculates the best overlay for a pair of molecules and outputs the RMSD between pairs of atoms, and MaxD, which is the maximum distance between a pair of equivalent atoms. The next three rows show how the quality of the overlay is improved if one of the molecules is inverted, the flexible torsion angles of one of the molecules are rotated, and if both inversion and flexibility are allowed before overlay. Note that during the overlay, rings are not flexed and hydrogen atoms are ignored. Let's start with an example using alanine, one of the proteinogenic amino acids. In the Cambridge Structural Database, both L and D enantiomers of this molecule are available. Open Mercury and navigate to the Structure Navigator tab on the right. Type the ref code LALNIN23 to load the L configuration. Then select multiple structures at the bottom and type the ref code ALUCAL05 to load the D configuration. Click the entry to display both structures. To access Molecule Overlay, click Calculate from the top-level menu and then select Molecule Overlay. A pop-up menu will appear. Select one atom from each molecule that you want to overlay and click Overlay. Since the two enantiomers cannot be perfectly overlaid on top of each other, the functional groups are pointing in opposite directions, even with flexibility allowed. However, by enabling inversion, once the stereocenter is inverted, allowing the molecules to be overlaid almost perfectly. Next, the tool can also be used to examine crystal structures containing two molecules in the asymmetric unit. Untick multiple structures and search for the ref code AADRIB in the Structure Navigator. This simple heterocyclic carbohydrate has two conformers of the same molecule in the asymmetric unit. Go into Molecule Overlay as previously, and once again select one atom from each molecule and click Overlay. The analysis reveals an imperfect overlay, which we can attribute to slight differences in bond lengths and angles between the two conformers, preventing a perfect overlay even when allowing inversion. The RMSD can be reduced a bit if we allow flexibility, which allows rotation around selective torsion angles. Still, the bond angles and lengths remain too different for a perfect overlay. Lastly, let's explore a high-pressure study. Search for the ref code NAKCIN01 in the Structure Navigator. This germanium compound was investigated under high pressure, at 9.4 gigapascals. You can verify this in the Structure Information menu. Select the molecule by holding Shift and left-clicking it. Then, right-click on the molecule, go to Color, and choose Red. If we tick multiple structures again, we can compare it to the crystal at ambient pressure, which has the ref code NAKCIN02. Color this molecule light blue in the same way as before, then calculate the molecule overlay. The overlay shows that the molecules are very similar, but the bromine atoms are slightly pushed toward the center of the molecule at high pressures. This doesn't change even when we allow inversion, flexibility, or both. Under high pressure, the bond lengths shrink and the unit cell contracts, so adjusting the torsion angles will not result in a better fit. This concludes our demonstration of the molecule overlay function in Mercury. Thank you for watching, and don't forget to subscribe to our YouTube channel.